Have you ever stopped to think about the air you're breathing? I mean, really think about it. It turns out it's not just empty space. It's a chaotic, high-speed ballet of invisible molecules. Today, we're going to pull back the curtain on the kinetic theory of gases and see the unseen forces that shape our world, from the pressure in your car tires to what temperature even is. So let's dive right in. Seriously, what's going on in there? You fill a tire with air, and suddenly it can hold up a 2-ton car. You blow up a balloon, and it gets firm and pushes back. Where does that force, that push, actually come from? Well, the answer is motion, a completely relentless, chaotic, and incredibly fast dance. We're talking about trillions of molecules zipping around, ricocheting off each other at hundreds of miles an hour. All that microscopic chaos adds up to create the world we can actually see and feel. Now, trying to track trillions of particles is, impossible. So to make sense of all this chaos, scientists came up with a brilliant simplification. They created a model called an ideal gas. It's not perfect, but it's an amazing tool for getting the fundamentals down. So let's look at the ground rules for this ideal world. Okay, so this model is built on 4 key ideas. First off, we pretend the molecules are just tiny, tiny points with no size at all. Second, they are always moving, completely at random. Third, and this is a big one, they totally ignore each other. No attraction, no repulsion, nothing. And finally, when they do hit something, the collision is perfect. It's elastic, which means no energy is ever lost. Think of it like a game of pool with perfect billiard balls that just never, ever slow down. And it's really important to remember this. An ideal gas is a tool. It doesn't actually exist in nature. It's a simplified version of reality that lets us nail down the basic physics before we start adding in all the messy, real-world complications. All right, so we've got these trillions of tiny particles bouncing around like crazy. But how in the world does that microscopic mayhem create the very real, very tangible force that we call pressure? Well, it all starts with just one collision. Picture one of these little molecules rocketing toward the wall of its container. It hits, bounces off perfectly, and completely reverses its momentum. And if you remember your basic physics, a change in momentum means a force was applied. And that force wasn't just on the molecule, it was also exerted on the wall it just smacked into. Now, of course, the force from one single molecule is so small you could never feel it. But here's the thing, it's not just one. It is trillions upon trillions of these tiny impacts happening on every square inch of that container, every single second. It's that collective, non-stop bombardment that we feel as pressure. And this all leads to a really powerful little equation that tells the whole story. It shows that pressure, P, is all about 2 things. How many molecules are packed into the space, that's the density, represented by rho, and how fast they're moving on average, which is v squared. So put simply, if you pack more stuff in, or you make the stuff move faster, the pressure goes way up. Okay, so pressure comes from collisions. But what about temperature? This right here is one of the most mind-blowing ideas to come out of the kinetic theory. It turns out temperature isn't some weird abstract property, it's a direct measurement of that molecular dance we've been talking about. When we measure the temperature of something, what we are actually measuring is the average kinetic energy of its molecules. That's it. Hot just means the molecules are, on average, moving faster. Cold just means they're moving slower. It's this incredible direct link between something we can feel, temperature, and the invisible world of molecular motion. And you guessed it, there's an equation for that. It's actually really simple and elegant. It says the average kinetic energy of a gas molecule is just a constant. That's 3/2 times K, which is Boltzmann's constant, a sort of universal translator between temperature and energy, multiplied by the temperature, T. For an ideal gas, this means temperature is the only thing you need to know to figure out the average energy of its molecules. Now that word average is doing a lot of work here. See, in any gas, you've got a whole range of speeds. Some molecules are moving insanely fast, a few are kind of lazy and moving slow, and most are somewhere in the middle. Physicists have a few different ways to talk about this spread of speeds, but the big takeaway is that one single temperature actually represents a huge variety of molecular speeds. Okay, let's put the pieces together. We've got pressure, which comes from collisions, and we've got temperature, which is all about motion. Now let's see how these microscopic ideas combine to give us one of the most famous and useful equations in all of science. And here it is, the ideal gas law, PV equals nRT. It's beautiful, right? It connects all the big picture things we can actually measure, pressure, volume, and temperature, with how much gas we actually have, N, the number of moles. This is basically the grand summary of how our perfect ideal gases behave. And what's so cool about this one equation is that it's actually got a bunch of other famous gas laws hidden inside it. For example, if you hold the temperature steady, you get Boyle's law. It tells you that if you shrink the volume, squeeze the molecules into a smaller box, the pressure has to go up, which makes total sense, right? They're going to hit the walls way more often. And the same goes for Charles' law and Gay-Lussac's law. The ideal gas law just wraps them all up into one tidy, powerful package. So far, we've been hanging out in this perfect, clean world of the ideal gas. But what happens when we come back to reality? How well does our simple model actually hold up? Right? So this is where our perfect assumptions start to break down a little. Real molecules aren't just points. They actually take up space. And they're not totally indifferent to each other. They have these weak little attractive forces between them. And because of those two facts, real gases don't follow that PV equals nRT equation perfectly. But this helps us understand exactly when our model works best. The ideal gas law is most accurate at high temperatures and low pressures. Why? Well, at low pressure, the molecules are so far apart that their individual size is basically irrelevant. And at high temperatures, they're moving so incredibly fast that they just zip right past each other, completely overcoming those weak little attractions. And that really leaves us with a final question to chew on. Our ideal model gives us the foundation, but the real world is always more interesting. Figuring out what happens when those little flaws in the model start to matter. What happens when the pressure gets crazy high, or the temperature plummets, and those molecules actually start to attract each other and clump together? Well, that's where the next deeper layer of physics really begins.